Hi everyone. As I mentioned in the previous video, I'm going to work through an example of calculating pressure in this case using the ideal gas and the van der Waals equation. So just remember that van der Waals equation is for real gas, and remember that we wrote down that equation in the previous video, so you should look back at your notes on that, but we'll write it back down again in this video as we're solving this problem. Okay, so the problem itself asks for us to calculate the pressure of ethanol at 82 degrees Celsius if you have 1 mole and it occupies 35 liters. And it's asking you to calculate it both ways using the ideal gas equation and van der Waals equation, compare your answers as a result, because remember that we want to see if is there a big deviation when we're using one equation versus the other one. So if I want to use the ideal gas equation, of course I have to write the ideal gas equation, which is PV equals nRT, and I'm just going to write it as P equals nRT over V because I'm being asked to calculate pressure. And if I substitute this, all of these numbers in here, which is 1 mole, R in this case of course is pressure volume, so we're going to use this value right here, 0.0821 liter atmosphere per mole Kelvin, and then we have our temperature, which is given as 82 degrees Celsius, and that's equal to 355 Kelvin. And lastly, we have our volume, which is 35 liters. So if you plug in all these numbers in your calculator, what you should get is 0.833 atmosphere. Okay? Now, that is if you assume ideal condition for the conditions that are given, which is 82, remember 82 degrees Celsius and the 35 liters, right? Now let's say we try to calculate the same situation with the real gas equation. So remember that the real gas equation is P is nRT over V, and then you subtract NB, which remember was the part that corresponds to the volume of the particles, right? And then from there we subtract that pressure from this other term, which is A N over V, and then the N over V is being squared. Now remember that that's the interaction term, the intermolecular interaction term. Okay, so let me just calculate these two components separately just so that I have space to make this calculation. So if I were to calculate the nRT over V minus NB first, I'm gonna just plug in the numbers here, 1 mole again for N, and then 0.0821 liter atmosphere per mole Kelvin, and then 355 Kelvin is my temperature, and then the denominator in this case is volume, which is 35 liter, minus the N times B. So N is 1 mole, that's just the number of moles. If you look back at the question itself, it tells you actually what the value of B is, and B in this case is given as 0.08407 liters per mole, so that's what I'm going to put in my numbers here. It's going to be 0.08407 liter per mole. So what you see is that when you multiply these multiply these two numbers together, the moles will cancel out, so that works out to be just liter at the bottom, so then you have liter subtracting with liter. At the top you have mole canceling and you have Kelvin canceling, and then of course at the end you have liter atmosphere on the top and liters at the bottom, so the liters will cancel, leaving you just with atmosphere. Okay, so that's what you have there in your calculation. You just have atmosphere for this term. Okay, and let's calculate that. So if you plug in all those numbers into the calculator, you should get 0.8347 atmosphere. Now remember that this is just the first part of the equation. Now I have to go and calculate the second part of the equation, so let's do that. So let's calculate that at the bottom here. So the second part of the equation is A N over V squared. The A value again is actually given in that question. So if you look back here, it shows 12.02 with the appropriate unit. So I'm gonna just copy that number here, 12.02 liters squared over atmosphere, and then mole squared. Okay. Now you notice that if you work this out with the units here, you have 1 mole of your gas, and then the volume, remember, is just the V that's provided, which is 35 liters, and you square this component. Okay, now you notice that what happens is if you work out the units, this mole squared becomes mole squared, and that cancel with the bottom mole squared here, and then the liter of course cancel with the liter square here, liter square also, so you're left again with actually just units of atmosphere. And I made a mistake here when copying. The atmosphere here should be at the top. Okay, so liter square atmosphere per mole squared. Okay, so then your N unit is just atmosphere in your answer, and I'm going to calculate this in my calculator, and what you find is that the answer is 9.81 times 10 to the minus 3, or another way to write it in decimal terms would just be 0.0098 atmosphere. Okay, so then what we have to do to calculate the pressure, remember from the initial equation, we're going to subtract this number right here that we calculated earlier minus this number. So I'm going to do that on the next page. So you have 0.8347 atmosphere minus the number we just calculated, which is 0.0098 atmosphere. And the result, if you do that calculation, is 0.825 atmosphere. Okay, so again, just to compare this with the ideal gas calculation, so this pressure is what you get if you were to use the real gas condition. If you assume that the condition that we're given is the real gas condition, you go back and look at the ideal gas equation calculation earlier. We had this number right here at the top, right, 0.833. So there is a difference in terms of value, as we expect. When we assume that this is real gas condition, the pressure is less than what we expect from ideal gas. And as far as which one to use, it really depends on the condition itself. For certain gases, that would be this condition that we're given in the question, which is 82 degrees Celsius, would be considered ideal gas condition, but for some other gases it would be considered real gas condition. It just depends on the gas that we're working with. Okay, but that hopefully shows you how to utilize this question. It's really just kind of plugging into the formula and calculating it. And this is the end of the gas topic, is this example right here.